Section 3.7, we're going to take a look at a topic called optimization. And if you'll remember what Chapter 3 was about, Chapter 3 was about applications of derivatives. Okay, so we were doing things like finding maximums and minimums, perhaps inflection points, things like that. Optimization has to do with maxes and mins. We're trying to optimize some quantity, make it like the largest profit you can have. Like that's a good thing, right? Sometimes we talk about making something the biggest value, or sometimes even making it the smallest value that you want to have for happening for something. So there's a few. This section feels a lot like it starts out like last section, which is 2.6. There's some processes that we go through. So sometimes there's a visual that you'll want to create. There may be a geometric image. There may not be, but a lot of times there is. Identify what quantities you know and things that you need to find. And this list of steps isn't something where it's like step one and I expect you to write out, step one and then do it, right? But this is sort of a reminder list of things that are going to be helpful. The third item in this list is to figure out what equations are applicable to your situation. What quantity is it that you're trying to optimize? What do you want to be the biggest or the smallest in this situation? And sometimes that means you have to change the equation a bit so that it has only one variable. Step 4 is to determine the maximum and minimum that we're allowed to have. That's not the maximum and minimum value that we're looking for, just what we're allowed to have. So, for example, if you're looking at, we're going to look at one that has an amount of fencing in an area. Well, fencing is a physical object. You only have so much of it. You don't have infinite amount of fencing. So there's a cap end on what you can actually use because there's a cap on what you actually have. Like these are physical quantities typically that we're talking about. There is an upper and a lower bound of what I can actually use. And then step 5 is to use calculus to find the extrema. So this is where we do things like take the derivative, set it equal to 0, find our critical points, look at sign charts. That's what step 5 is talking about. Okay. All right, so we are going to start with one that does have fencing. This one is a 3-sided fence. A 3-sided fence is to be built next to a straight section of river, which forms the 4th side of a rectangular region. The enclosed area is equal to 1,800 square feet. Find the minimum perimeter and the dimensions of the corresponding enclosure. So, without even having done so, you probably are picturing something in your mind because this has a visual representation, right? You got a river. So here's my river over here. And it says I have a 3-sided enclosure. What shape am I drawing here? Am I going to draw a triangle? Because if I draw a triangle, I only have 2 sides because I'm not fencing alongside of the river.
Like a backwards C?
I don't think so.
It says rectangular.
Rectangular, right? So we're talking about a rectangle. Rectangle's 3 sides with the river. We're not enclosing along the river is the description that we're given.
Backwards C.
It's a backwards C. Is that what you told me before? I heard you say Z as in the letter Z, and I was like, that'd be an interesting enclosure, a letter Z. Yes, we'll go with a backwards C, a very boxy one, right? Yeah, okay. So there's some things that you know about rectangles. So tell me something that is helpful in this diagram about the rectangle shape. Related to our problem. There's several things you know about rectangles.
Area is length times width.
Area is length times width. So how about we call this our width and we'll call this our length. And the area is length times width. Or if you don't like L and W, use X and Y. It doesn't matter what letters you use, right? That's a helpful piece of information about the shape. What else? What about this piece down here?
That's also W.
It's also W, because we're talking about a rectangle, right? And the opposite sides of a rectangle are equal in length and or width. There's another quantity that's mentioned in the problem that we need to make sure that we're addressing. What quantity is that?
Area.
Area is already on there.
The other length.
We've already written the other length. One more. Perimeter. The question talks about perimeter. Now, we don't have a complete rectangle here, right? We only have a 3-sided rectangle because the other side, we're not fencing along that side. And you might be thinking like, well, why would you do this along a river? Don't really have a great answer, but if it were along the side of a barn or a fence that already existed, can you understand why you wouldn't necessarily need all 4 sides? Yeah. So like our house, we have a fence around our backyard, but we have a neighbor that doesn't. If he wanted to create an enclosure in his backyard, he wouldn't need to fence along the side that's already part of our yard, right? It's already there. He would just have to tie into it. Okay. All right. So what would perimeter look like since I don't have a full rectangle here?
Would it just be 2 times W times, or plus L?
Yeah, it would. And you may not like the phrase that it's called perimeter, because perimeter is supposed to be, the distance around all the shape. But if it helps you to think of it, what we're really trying to figure out here is the amount of fencing, right? So if you don't want to call it perimeter, don't call it perimeter. But the fencing itself has to be added up this way. I have 2 W lengths and I have an L length. Okay, so we're good so far. There is a piece of information that we haven't used yet from the problem that was given to us. Do you see it? What piece of information have we skipped over at this point?
Area,
Which is,
1800.
yeah, they actually give us the area of our shape, right? Now that's a little bit different. A lot of times they will give us the side lengths, or they'll give us the perimeter, or the amount of fencing, and then we find the area. So this one's set up a little bit backwards of the way they're sometimes set up. That's okay. What that tells us is that this A right here is not a variable. I know what it is. It's 1800. So this is 1800 equals L times W. And what does it say I'm trying to find the optimal value of? What am I trying to optimize? The perimeter. It says right here, I want to find the minimum perimeter. Minimum is a word for optimization. Minimum and maximum. So anytime you see that word optimization, you're thinking mins and maxes. So this is the quantity I'm trying to find the optimal value of. In this case, the minimum value. Now, does it make sense that you would want the minimum amount of fencing? Well, yeah, because fence costs money, right? I don't want to have a lot of extra fence left over that's just, cluttering up my yard and cost me money to do so. So we're trying to find an amount of fencing that's the minimum amount for our cost. I mean, what we're really trying to minimize probably is cost, right? So the amount of fencing is the equivalent of the cost. So we're trying to find the minimum perimeter. And to find minimum, what we're trying to do is we're trying to use this calculus, right? But there's a step that's 2 steps before that we haven't accomplished yet. What was step 4? 3. What does it say I need to do?
Write the equation in terms of 1 variable.
I need to have only 1 variable, and right now there are 2. I have a W and an L, correct? So I need to adjust this equation so that I don't have a W and an L. Can anybody see a way that I can do that? I'll give you a hint. It involves this equation. What can I do with that equation so that I don't have a W or I don't have an L? And I don't care which one we choose. But I don't want one of them.
Divide by 1 of the variables.
Yeah, it can divide by one of the variables. Dylan, since you said it, you get to pick.
L.
L, all right. So we're going to have 1800 divided by L is equal to W, which means I can take this quantity for W now, right? Whoops. And I can substitute it in right here. And I'll only have L's left. I won't have any more W's when I do that. So this perimeter will equal 2 times 1800 over L plus L. I'm going to multiply the 2 and the 1800, but I'm also going to bring my L up because finding a derivative when the quantity is up is easier than when it's down, right? I don't have to use a quotient rule that way. So what's 2 times 1800? 3600. I'll have L to the negative 1 plus L, and that's my equation now for the amount of fencing, or what we're calling P, or perimeter. So what do I have to do next with calculus to find the optimal value of this? I take the derivative. I need to find the derivative of P. So what's the derivative of 3600 L to the negative 1?
Negative 3600 L to the negative second.
Yes. And what's the derivative of the, yeah, plus my 1. So if I rewrite this just a bit, this is negative 3600 over L squared plus 1. Everybody good? Have a derivative. What do I do with the derivative? I set it equal to 0 or equal to does not exist. Where does this not exist? It does not exist at 0. Okay, so keep that in mind as an option. But there's one more thing that we're going to do before we continue on, and it doesn't necessarily have to be done next, but it's listed next in my order of steps. We haven't done step 4 either. Step 4 says to determine the maximum and minimum allowable values for L. Well, we're using L because we've eliminated W. It doesn't really matter which one's left, but whichever one's left. So obviously L can't be 0 anyway. What would happen if L were actually 0 here?
There would be no area.
There would be no area, right? So L cannot be 0. That doesn't make any sense. It has to be more than 0. So kind of a note up here is that L is bigger than 0. Is there an upper end? What's sort of the maximum value that seems like a reasonable thing to say, I can't go beyond this?
1,800.
Yeah, maybe like an 1800. Now that may not be exactly right, but it gives you an idea. Because if the L were actually 1800, the W's would be 1, and technically you could still have an area, but you'd have this tiny little skinny rectangle. That's not going to give you a good situation for your perimeter, right? It's going to give you a really, really long rectangle. Okay, it's 1,800 square feet. That's fine, but that's definitely not going to be the smallest amount of fencing. So this is certainly an upper bound. I mean, there's a bigger number than this is not going to happen. So this gives us a good idea of where we could be looking. Okay, so we're right that this is 0 or does not exist. Does not exist gives me the 0, but the 0 is not allowed anyway. Okay, so equal to 0 means that I would have 3,600 over L squared plus 1. Actually, let me do it this way. Equals negative 1. So we'll move the negative 1 to the 1 to the other side. They're both negative, so we can cancel those and make them both positive. Can also multiply by L squared. So I do that, let's move it up here. So I'd have 3,600 equals L squared if I multiply both sides by L squared. What will L be in this scenario?
Minus 60.
Positive or negative 60. Now, can they really be positive or negative 60? No.
You moved it like that way.
You can't have a negative length.
You could try.
No, you can't. No negative lengths. You can't. So while the algebra gave us 2 possibilities here, the context for the problem eliminates one of them. And that will happen sometimes. Not always, but sometimes. So 60 is the prime possibility. If you want to think about it here, I'm capped between 0 and 1,800 on the ends of this thing. And somewhere in between, not drawn to scale, of course, is a 60. What do I do with my sign chart now? Y'all remember? I pick a number, between them. So what's a number you might want to pick between 0 and 60? 20, okay. And between 60 and 1800? 100. Fabulous. What are we going to do with the 20 and the 100? We're going to plug them into the derivative. Right. So the version of the derivative that's probably the most conducive to doing that would probably be this one, although you could use the version before if you wish. So if I put in the number 20, I have 3,600, negative 3,600 divided by 20 squared plus 1. Do I get a positive or do I get a negative? I get a negative. What about if I put in 100? Negative 3,600 divided by 100 squared plus 1. I'll get a positive. Okay, so I know it's been a minute, but negative means it's decreasing. Positive means it's increasing. So what is this point? It's a minimum. What was I looking for? I was looking for a minimum, right? Now, we have found the value for L. L is 60 to give me the minimum, but we need to make sure we answer the question asked. What was the question asked in this problem? Minimum perimeter. Have I found the minimum perimeter? No. And I've actually asked me two things, find the minimum perimeter and find the dimensions. So I haven't found either one of those things yet. I have found part of the dimensions. One of the dimensions is the length of L, 60. So L is 60. We're in feet, right? Yeah. 60 feet by, what's W if L is 60? 30. How'd you get that? There's a couple of ways, is why I'm asking. Okay, you can put it into this equation directly. 1,800 divided by the 60 would give me the 30, right? You could also go back to the original problem and think about it from the perspective of this particular diagram, more of a visual perspective instead of an equation perspective. So these are the dimensions. That's part of the question. How do I find the perimeter?
2 times W plus L.
Yeah, so I'll write it over here, 2 times W plus L, that was my perimeter. So my W, we just found out, was 30, right? So 2 times 30 would give me 60, and then another L would give me, for the value L was 60. So I get a perimeter of what? 120, thank you. You guys don't want to talk to me today. The perimeter is 120 what? Feet. Right? Perimeters in feet, just like the dimensions are in feet. If area was what we were looking for, like it was given, that's square feet. Okay. These are long problems. They just are. So let's take a look at a couple more examples. This is a classic example. Every calculus class is going to have this question in it, every single one. The fence one is too, or at least some version of it. We have a box with no top. So imagine like a shoebox without the lid, or a t-shirt box without the lid, something that has no lid. Take the donut box without the lid, okay? So you've got a box with no top. It's going to be built by taking a 6 foot by 10 foot, inches, 6 inches by 10 inch sheet of cardboard and cutting X inch squares out of each corner and folding up the sides. All right, so we're going to draw a picture of such a image. So here's my 6 foot, and I'm going to label it, not foot, I still keep saying feet for my last problem, 6 inch by 10 inch cardboard paper. And I'm going to cut corners out. So if I cut the corners out, it looks something like this. That wasn't what I meant to do. So there's a corner that's cut. there is an x inch square, x by x inch square, cut out of each corner like this. Okay, so you're actually going to cut along these dotted lines, right? These corners will not be here any longer. If it helps to imagine it, you could actually imagine drawing this so that you erased the corners, right? I won't erase them all, but this is the picture. And then you're going to fold along these uneven sides. I'll erase this other one so you can see the fold. So now you're going to fold along this dotted line and along this one and this one and this one. So can you picture it? This little piece flap, this little flap at the bottom folds up, and so do all the other three. And it creates a box. You'd need like tape on the corners or something, right, to make it actually hold. This creates a box. We would like to find the corner that we need to actually fold and cut and remove, right, and to create the folds, so that we have the largest volume, right? Volume is the amount of space inside, a three-dimensional space, right? So you can picture, the donut box or the t-shirt box, and they're really short and thin, correct? Because the corners that have cut out have been little. But if you cut out a bigger corner and it folds up in a bigger way, you get more like a shoebox kind of shape. Right? Shoebox holds more volume than the t-shirt box does or the donut box does. That's our picture that we have. And we have to figure out what that little corner that we're cutting out, this little square in each corner, what size it is to give us that biggest volume that we want. All right, so what are some formulas that we're going to have to use for our box, for all this description? The area of a square might be a possibility. So what's the area of a square?
4 times the side.
So we have,
Side squared.
okay, be careful. Where are our squares? Let me say that first. What squares do we have in this shape? Just the corners that we cut out are the squares, right? Just the corners that we cut out are our squares. What other shape do we have then? It's a rectangle on the inside. So there's a rectangle on the inside. And we're actually not finding area of all these shapes, but the volume. So we probably want to actually look at volume instead of area, the way that the problem is set up. Although we will have to talk about the area of these corners, or at least the dimensions of these corners as we make this claim, right, moving forward. Okay, so what is the volume of this rectangular box? How do you find volume?
Length times width times height.
Okay, so everybody remember that one? Okay, again, that's one of those ones that you really should know that one. If I were talking about the volume of a cylinder, probably give you that formula, right? So some shapes we are going to say are very familiar to us, others are less familiar, we don't use them quite as much. Okay, well, believe it or not, with the exception of the fact that I haven't written in the X's here, because these were lengths X that I folded along, this picture now has everything I need to figure out what the length, the width, and the height of this box are. Let's start with the height. Can you tell me what the height of the box would be when we make these folds? It's X, right? I'm folding this piece up, and it's of length X because this cutout was of length X. That's the easiest one, that the height is X. How about the length and the width?
10 minus 2x and 6 minus 2x.
Okay, so the length visually would be this piece, right? It started out top to bottom as 10, but then I've cut off 2 pieces, so you're exactly right. This would be 10 minus 2x. And by exactly the same reasoning, this would be 6 minus 2x. So my length is 10 minus 2x, and my width is 6 minus 2x. So my volume equation looks something like this, which we'll multiply it all out in a minute. But Now, the good news is this equation only has one variable to start with. I mean, it's got two because it says volume equals, but the other side of it, the part we're going to try to maximize or minimize or whatever we're looking at, optimize, has only one variable. Okay, so that's good news. I need to kind of look at the upper and lower ends of this thing. X is my variable. What's the smallest and largest X can be in the context of this problem? Start with smallest.
0.
0. It's got to be bigger than 0 or there's no volume, right? If I don't have a bigger than 0, I didn't make a box. It's still just a sheet of paper. What's the biggest it could be?
6.
Smaller.
5.
3.
4.
3.
3.
Why is the biggest it could be 3?
Because anything smaller than that would, no, anything bigger than that would make the bottom side equal 0 or less.
Right. The length of the bottom or the width of the box is 6. I can't cut away more than 3 inches and still have a box, right? So that's my upper end. I am trapped between 0 and 3 for the solutions I'm going to get for my corners that I'm cutting out. All right. So we're going to clean this up a little bit. I have 60x, that's negative 12, and negative 20, so that's negative 32. It'll be x squared because I'm multiplying by the x at the end, and then we have a positive 4x cubed. I believe that's right. Does that look okay to you guys? I've got 64. Oh, sorry, there was 2 of them. Or is there? Look on this paper. I think that's right. Okay, are we good? All pieces in there? And we want to set this, or not yet. We want to find the derivative of this, right? So we're going to need the derivative of this. So what is the derivative of 60x? How about the derivative of negative 60, negative 32x squared?
64x.
Yeah, negative 64x. And then 4x cubed? 12x squared. Yeah, 12x squared. You might notice at this point, all of these are multiples of 4. Do you see that okay? So we could actually, we're going to set this equal to 0 in a minute anyway, so we could just divide everything by 4 to make it smaller to work with. I'm all about making it easier to work with. This would be 15. That would be 116x, and then 3x squared. Does that look right? Okay. All right, so I'm going to spoil the fun a little bit and tell you this doesn't factor. That's what we would do try first, right? We would try to see if this would factor. It's not going to work. So if you get to the point where factoring is not an option here, what would I need to do then? There's 2 choices. Okay, the one we're not going to go with is called completing the square. Do you have an idea, Dylan? Quadratic formula is the one we are going to go with. So when I've got a quadratic and it's not going to factor, the most direct way typically to do the problem is to use the quadratic formula. So x equals negative b, that would be the 16, plus or minus the square root of b squared, so negative 16 squared, minus 4. A is the x squared term, so that's the 3, times c, which is my constant term, 15, over, all over 2 times a, which was 3. Okay, so typically we like to keep things super exact in math, right? We would look for the square root version of the simplified pieces of this and so forth. But this problem is a context question, correct? Like we're literally going to cut a length out of a corner of a box. Yeah? What that means is I really want a decimal value for this for it to make sense in the context of the question. So your calculator can be used to find two quantities for this very quickly. The two quantities are 4.12 and 1.21. But one of those I can't have. Which one? 4.12. Why? It's bigger than 3. It will not create a box. If I cut off 4 inches of one corner, I don't have a box anymore. So, in terms of a sign chart, the only number that goes on my sign chart is going to be the 1.21. So, I've got my end caps at 0 and 3, and I have a number 1.21 in between. What's a value I can test before 1.21? 1. After? Probably 2. And where do I test those numbers? In the derivative. And I can use either the 60x minus 32x squared plus 4x cubed, or I can use the one where I divided out the 4. It won't change it, right? Because I divided by a positive number. That doesn't change anything. So either of these that you put this into, what you find is that this first one is positive, and the second one's negative. Positive, negative looks like that, right? Increasing, decreasing. So what is this point? It's a maximum. So our x value is 1.21, and it's 1.21 inches because the problem was in inches, but we need to make sure we answer the question that's asked. What question is asked? So it actually says find x, right? Find the value of x. So on this question, when I get to this point, I'm really done. I have found exactly what I was supposed to find. But could it have asked me something different? Sure. It could have asked me, what are the dimensions of the box? It could have asked me, what's the volume that this is going to create? So we want to make sure that when we look back at the question, we're really answering the question that was posed in the problem. Okay, last question. This one has a visual, but it's not a visual that's like the ones we've been doing. It's not a physical object in quite the same way. It says it wants us to find a point on a curve that is the closest, the curve is y equal x squared, that is closest to the point 0, 1. What does this curve look like? It's a parabola. So our shape that we're drawing is a graph. It's the graph of a parabola. Looks something like this. And it references the point 0, 1, which would be something like this. Now you can probably tell me things that don't work here. For example, the point that will be the closest point is not over here. That is not the closest point to the red point I started with, right? There's no way. It doesn't make any sense. So it's got to be somewhere close to it. So somewhere like here, or like here, or like here, right? It's got to be sort of in this neighborhood of values that visually are close to 0, 1. And in fact, because we have a parabola, and we know a little bit about the parabola's equation being y equal x squared, we know right here this point is at 0, 0, right? And so that means that the distance from the point down to the origin, right here, this is a distance of 1, correct? And we know if we go straight out to the side, we have the same thing happen. Because this point would be at the point x equal 1 as well, same height, right? Well, I should put it this way, y equal 1, same height. And because y is equal to x squared, it's the point 1, 1. And the same is true over here. We have the point negative 1, 1. So these 3 points sort of seem to sort of encapsulate everything beyond this is bigger. The answer has to be somewhere in between here. Does that visually make sense? You might think, well, I bet it's about halfway. Maybe it's at x equal 1/2, and maybe it is. But we need to justify that it is or it isn't, and I'll tell you it's not. But it's a reasonable looking thing to say it's probably about halfway, right? And it is in between. So how do we find distance? Because there is a value here, and then there's going to be two of them, because whatever it is over here, it's going to be over here as well, correct? Whatever, there's going to be 2 points that are going to be equidistant. How do I find the distance between that blue point and the point that I was beginning at, 0, 1? How do you find distance?
Is there like a formula for that?
There is a formula for that, yeah. The distance formula looks like this. I'll just write out the general one that you've seen before. And you might have seen the subscripts written in reverse order. That's fine, it doesn't matter. You subtract the x values, you square it. You subtract the y values, you square it. You add those quantities together, and you square root. So we need to figure out what our values are. Well, this point right here, we know. It's the point 0, 1. So one of my x values is 0, and one of my y values is 1. Make sense? So in terms of this equation, I'll just let that be my second point. This is 0, and this is 1. I need to find the other point still, but we're sort of halfway there in determining the pieces. Now, I don't know what this point in blue is. That's kind of what I'm looking for, yeah? I don't really know what it is. It is some point, and I don't know the x value. But whatever the x value is, what would I have to do to find its corresponding y value? I have to square it. So whatever x is, y is squared, because that's the equation of the curve I'm on. So whatever the equation you were given, you would do the same thing. There's nothing special about the equation of y equal x squared. This is just the specific value for this one. So up in my formula, the x is just x, but the y is x squared. And again, I now have an equation in only one variable. My limits, right? Like what are sort of the capping ends of x? What's the minimum that x seems to be able to be? Like the x is the x value in this picture that I've drawn here. Yeah, it looks like maybe -1. And what does it look like the maximum seems to be for x? 1. These appear to be sort of my upper and my lower bounds for what I'm looking between. Okay, cleaning this up just a little bit. This one, x minus 0 squared, is just x squared. To do the other piece, sorry, I can't get high enough to point to it, but to do the other piece, I have to square a difference, right? It's x squared minus 1 times x squared minus 1. So you're going to distribute FOIL, of those kind of things, multiply it all out. And so we're going to end up with x to the 4th. This is negative x squared and another negative x squared, so that's negative 2x squared. And then plus 1. It's already looking better. I can combine, of course, these two here so that it can change into x to the 4th and then minus just x squared and plus 1. And that's my equation for distance in this case, the distance between these 2 points. And I am trying to minimize the distance, right? I'm trying to find the shortest distance out from that particular point 0, 1. So what do I have to do next? Derivative. So the derivative of this is a chain rule, right? I've got a square root on the outside, so that's a power 1/2. I rewrite the inside to the power negative 1/2. And then what's the derivative of the inside?
4x cubed minus 2x.
Yes, 4x cubed minus 2x. We can simplify this a little bit, namely this 1/2 can simplify with the 4 and the 2 here. We can put the negative 1/2 as a square root in the bottom. So on the bottom, I'm going to have my square root of x to the 4th minus x squared plus 1. On top, I'm going to have 2x cubed minus x. And we would set it equal to 0 or does not exist. The top actually will equal 0. So if I have 2x cubed, maybe I should mention the bottom actually won't equal 0. It does not have that ability, but the top does. So if I have, minus x equals 0, I can factor this, pull out an x. I have 2x squared minus 1. This one is x equals 0. This piece right here would give me 2x squared equal to 1. X squared is 1/2. And I put the square root on, so x is equal to positive and negative square root of 1/2. Generally, we don't leave it written that way. We would rationalize the denominator. So we would end up with positive and negative square root 2 over 2. Which should feel like a value you've seen before if you took trig. Have you seen square root 2 over 2 before? Where have you seen it?
Circle.
On a unit circle. You have seen it on a unit circle. Yes, indeed. At the angle measure of pi over 4, otherwise known as 45 degrees. And can you picture that that's exactly what's happening here? That's making two 45-degree angles? It's split it in half, just not giving you an x value of 1/2, right? So our intuition that it's somehow halving things is correct. It just didn't yield us an answer that was x equal 1/2, right? The angle was cut in half instead. Okay, really quick, what we would need to do is we would need to check a number line to make sure that this would work. We cap it at the ends at -1 and 1. We have the 0 in the middle, and these values of square root 2 over 2 negative. And this is so not running into everything, right? It's fabulous. It's better. And then square root 2 over 2 here. We would test points in between. Let me just cut to the chase and tell you this one's negative, positive, negative, negative, positive. So negative, positive, negative, positive. And I'm trying to minimize the values. So these are, in fact, my minimum values. It wants to know, however, the point, or in our case, we're going to have points closest. And these are both x values. Agreed? How do I find the y value in this equation if I know the x values? You square it. So the values actually end up being negative square root 2 over 2 and 1/2. So there's that 1/2 showing up. The y value is 1/2. And positive square root 2 over 2 and 1/2. And again, those 1/2s are coming from squaring the square root 2 over 2, which was the same as the square root of 1/2. So squared is 1/2.